Welcome back to the deep dive.
Always great to be back.
Today we're diving into something pretty big, titans. Learning to memorize at test time.
Sounds epic.
It is, actually. It's a paper exploring a whole new way of thinking about neural long-term memory modules.
Memory and machine learning. Always a tricky one.
Exactly. And this has big implications, not just for ML folks, but also for data scientists, even mathematicians.
I can see how it would cross those boundaries. So where did this paper pop up?
It hit ArcCiv on December 31st, 2024.
Recent stuff, then. And who are the minds behind this?
Researchers Ali Behrouz, Peilin Zhong, and Vahab Mirrokni.
Okay, I'm intrigued. Why is this paper making waves? What's the core problem it's tackling?
It's all about dealing with sequential data, right? Like text or time series.
The classic problem. And the usual suspects are recurrent models and attention mechanisms.
Yeah, but they both come with their own set of problems.
Oh, absolutely. Baggage galore.
With recurrent models, the problem is that they process data step by step and build up this hidden state.
Right, like a compressed memory of everything that came before.
But the size of that hidden state is fixed.
There's the rub. So as your sequences get longer, it's like trying to, squeeze the entire ocean into a teacup. You're bound to lose something important along the way.
Exactly. And then attention mechanisms came along and people were like, this is the solution. They can look back at the entire input, focusing on what's relevant at each step.
That's the beauty of attention, right? Direct dependency modeling between tokens leads to much more accurate results.
But there's always a but.
Computational cost. Oof, that quadratic complexity can be a real killer.
Meaning, for those of us who don't live and breathe the complexity theory.
Basically, the resources needed explode as the sequence gets longer. So in reality, you're still limited to fixed length contexts.
Right, so we're stuck between a rock and a hard place. Recurrent models struggle with long sequences, and attention mechanisms hit a computational wall. So where do these titans fit into this whole mess?
That's where this paper gets really interesting. They've introduced a new neural long-term memory module. It doesn't try to cram everything into a fixed size hidden state or rely solely on attention with its limited reach.
So how does it work?
This module learns to memorize the historical context. It allows the model to tap into information that's much further back in the sequence.
So it's not just about remembering what happened recently, but actually retaining and using data from way, way back.
Exactly. The paper makes this clever analogy think of attention as short-term memory, and this new neural memory module as long-term memory.
Okay, I'm with you. So attention with its limited context, but precise dependency modeling is like our short-term memory, good for recent stuff. And this neural memory module is like our long-term memory. Maybe not as precise, but it can store vast amounts of information for much longer.
Precisely. And it's the synergy between these two memory systems that leads to the Titans family architectures.
Wait, family, so there's more than one Titan?
Oh yeah, there are 3 Titan variants presented in this paper. Each one incorporates memory a bit differently, but they all build on this fundamental interplay of attention for the short term and the neural memory module for long-term needs.
So it's like a team of Titans, each with their own specialized memory skills.
Yeah.
That's cool. But do they actually deliver? How do they perform in real-world scenarios?
The researchers didn't hold back on the testing. They put the Titans through the ringer. From language modeling and common sense reasoning to even genomics and time series analysis.
Wow, a real gauntlet.
The Titans consistently beat both transformers and those fancy new linear recurrent models across all the tasks.
Impressive.
But here's the kicker. They can handle context windows larger than 2 million tokens.
2 million? That's insane. What does that kind of scale allow for?
Think about those needle-in-haystack tasks. Finding a specific piece of information buried in a massive data set. The Titans are phenomenal at that. Their accuracy with such huge amounts of data blew all the baseline models out of the water.
So they're not just powerful. They're incredibly efficient at finding what they need within enormous data sets. This opens up a whole new world, doesn't it?
And absolutely. The Titans, with their short-term and long-term memory, have the potential to revolutionize how we approach research and applications in fields that deal with sequential data. This is a big leap forward.
It definitely feels like we've only just scratched the surface here.
Yeah.
Let's pause for now and come back to unpack the specifics of these Titan variants in the next part of our deep dive.
Yeah, we've only just begun to explore what these Titans can do. I think it's time we go deeper into the heart of this innovation, that neural long-term memory module.
Absolutely. That's where the real magic seems to happen.
Yeah.
Right? Tell me, how does this module actually learn and retain information over such huge stretches of data?
Well, at its core, it uses a totally new memory structure. It allows for persistent storage of historical context.
Persistent storage. So we're not talking about compressing or summarizing information like in those recurrent models, right?
Right. This is about holding on to the data itself, but in a way that you can retrieve it efficiently later on.
So it's more like having a massive library where every single piece of information is meticulously indexed and ready to access whenever you need it. But how does this all work with the attention mechanism? Are they constantly interacting?
The interplay between attention and this long-term memory is it's dynamic and intricate. Attention, that's your short-term memory, focuses on the most relevant recent information. And then the long-term memory module kicks in when you need context from further back.
So it's not about replacing attention altogether. It's more like giving it a powerful partner.
Exactly. They work together, each playing a crucial role in processing that sequential data.
Got it. Now, you mentioned there were 3 Titan variants in the paper. What makes them different from each other?
Each one tackles the interplay between short-term and long-term memory in its own way. It's like they each have a unique approach to dealing with sequential data.
Okay, walk me through them. What sets them apart?
The first one is called Titan LM. This one is designed specifically for language modeling tasks.
Makes sense.
And it uses this unique strategy where the long-term memory module is actually integrated directly into the transformer's feed-forward network.
So it's not a separate module. It's woven right into the fabric of the transformer itself.
Right. And that integration allows Titan LM to leverage those long-range dependencies within the text.
And that leads to
Significant improvements in perplexity and accuracy.
perplexity, right?
Yeah.
That's basically how well the model predicts the next word in a sequence. Lower perplexity means it's doing a better job.
Exactly. Now, the second variant is Titan G. This one's specifically for genomics tasks.
Genomics.
Yeah.
Talk about needing to handle huge amounts of sequential data. That's a prime example.
Oh, absolutely. And Titan G handles this a bit differently than Titan LM. It keeps the long-term memory module separate.
Okay, so what's stored in that module? The entire DNA sequence.
It's actually more clever than that. It stores what are called comers. These are short, overlapping subsequences of DNA extracted from the input sequence.
So instead of storing the entire sequence, it breaks it down into these smaller, meaningful chunks, the comers. I guess that makes it easier to manage those super long sequences.
Right. Storing comers makes the representation of the genomic data more compact and efficient. And that means faster retrieval and comparison when you're doing analysis.
Makes sense. Now, what about the third variant?
Yes. The third one is Titan Time, and it's built for time series analysis. This one uses a new mechanism called temporal chunking.
Temporal chunking. Interesting name. What's that all about?
Basically, the long-term memory is divided into these chunks, each representing a specific window of time.
So instead of continuous flow of data into the memory, it's segmented. How does that help with time series data?
Well, it allows Titan Time to selectively access information from specific periods in the past.
Oh, I see. So if you're trying to forecast something or detect anomalies where understanding the patterns over time is crucial, this kind of selective access would be really valuable.
Exactly.
So we've got these 3 Titan variants, each tailored for a specific type of sequential data. But the underlying principle is the same, that strategic combination of short-term attention and this new long-term memory module. Did the researchers actually put these variants to the test in real-world applications?
Oh, yeah. They ran extensive experiments. They wanted to see how each Titan variant performed. For example, in language modeling, Titan LM achieved state-of-the-art results on several benchmark datasets. It actually outperformed Transformer XL and other recurrent models.
So it's not just a theoretical concept. It actually works better in practice, at least for language modeling. What about the other variants?
The other variants performed really well, too. Titan G showed superior performance in various genomics tasks, like gene expression prediction and protein classification. And Titan Time, well, it was a star in time series analysis, things like forecasting electricity demand or predicting stock prices.
So across the board, these Titans are really living up to their name. They're pushing the boundaries of what we can do with sequential data. This has to have some serious implications for the future of machine learning and data science as a whole, don't you think?
Absolutely. This paper opens up a whole new way of thinking about the role of long-term memory in machine learning. It challenges the traditional focus on short-term context and paves the way for more powerful and efficient architectures that can handle the increasingly complex data we're dealing with.
It sounds like we're on the verge of a paradigm shift. The Titans are leading the charge, and I, for one, am excited to see where this all goes. But before we get too far ahead of ourselves, let's take a pause here. We'll wrap up our deep dive into Titans, learning to memorize at test time in the next part, where we'll talk about the potential impact and future directions of this groundbreaking research. Welcome back to the deep dive. We have been exploring Titans, learning to memorize at test time, a paper that's really shaking things up when it comes to processing sequential data.
Yeah, it's been a true deep dive, that's for sure. Uncovering all the ins and outs of this new architecture and how it could change the way we deal with these complex data sequences.
And as we wrap up, I think it's important to step back and consider the bigger picture, the impact of this research. These Titans, with their unique approach to long-term memory, they're not just theoretical, right? They have the potential to change real-world applications across all sorts of fields.
Absolutely. The ability to learn from and analyze such massive amounts of sequential data and to do it with the efficiency and accuracy that the Titans have shown, it opens up a whole world of possibilities.
It does.
Take healthcare, for example. Imagine using a patient's entire medical history, every test result, diagnosis, treatment, to personalize their care in a way that we can only dream of right now.
Like having a medical AI that understands the full context of a patient's journey, not just bits and pieces.
Exactly. And what about the implications for scientific research? I mean, the potential there is huge.
I can only imagine.
We could analyze decades of climate data to get a much deeper understanding of climate change patterns, develop better strategies to deal with it, or imagine looking at astronomical observations going back centuries to try to unlock the secrets of the universe.
Wow. So many possibilities.
Yeah.
And it all comes down to this fundamental shift in how we think about machine learning models moving beyond the limitations of short-term memory and embracing the power of long-term context.
The researchers actually drew inspiration from human cognition itself, the way our short-term and long-term memory systems work together.
They're pretty amazing.
They use that to create a more powerful and efficient architecture. It just shows you the importance of thinking outside the box, looking beyond your own field for inspiration.
Definitely. This paper really highlights how innovation often comes from unexpected places. It encourages us to explore those seemingly unrelated fields, looking to nature, human behavior, even the arts, for new ideas.
It's all about challenging the status quo, being open to different perspectives. That's how we discover new possibilities and pave the way for the next wave of breakthroughs.
And who knows, maybe one of our listeners today will be inspired to build on this research, create even more powerful and sophisticated Titans, pushing the boundaries of what's possible in machine learning even further.
Now that would be something to see. As this research keeps developing, I can't wait to see the impact it has on our world, to see the incredible applications that emerge from it.
It's a future full of potential and possibility, and the Titans are leading the way. We hope you've enjoyed this deep dive into Titans, learning to memorize at test time. We encourage you to check out the paper yourself and think about how these groundbreaking findings might impact your own work or spark new ideas in your field.
Until next time, keep exploring, keep asking questions, and keep pushing the limits of what we know, because the journey of discovery never truly ends.